thank you so much for your kind introduction, and I'd like to thank all organizers for inviting me to this wonderful conference. And I used to be working on the quantum chemistry reaction dynamics on HPCs, and I kind of moved to the quantum computing sector. And I'm very excited about coming back to this community in the context of hybrid quantum and hybrid HPC and quantum computing. So I personally am working on chemistry, but today, on behalf of the hybrid system development project team at Quantinuum, led by Ross Duncan and Alex Chenoksov, our team, I'd like to talk about Tierkreis, the hybrid workflow system. Okay, so before jumping into the main topic of today, I'd like to share some context so that you can understand why we are doing this. So as Matsuoka-sensei mentioned yesterday, and Tsuji-san also mentioned yesterday, we, Quantinuum, are working closely with Kent in development and application of the hybrid system. So as you see on your right, our hardware team, consisting of the joint Japan and US team, is now working on installing the Quantinuum trapped ion hardware in Riken Wako campus, and it's going to start operate in the next months. And on top of that, our software team based in the UK is working closely together with Sato-sensei and his group, developing the hybrid system software to connect Fugaku and our quantum computer closely and efficiently. And further, on top of that, we are working with the software team more on the application side, consisting of the UK and Japan-based team, including myself, to use this efficiently connected hybrid system more on the application side. And today, I will focus on this application perspective rather than the hybrid system itself, and focus on the Tierkreis to efficiently drive the hybrid system in a workflow context, as Tsuji-san mentioned yesterday. Okay, so let me continue a bit of context. So recently we are talking about quantum classical and hybrid system, but because quantum computers are very different from usual classical computers, I think let me take this chance to talk about what does a quantum classical hybrid system look like. So the keywords are these two: large compute and small data. So because quantum computers are very good at a specific task, we need to make the hybrid system very useful, we need to be aware of what the quantum computer is good at. So the large compute, as many of you know, there is a known algorithmic speed up in quantum computing. In the best case, we can expect some exponential speed up like in quantum phase estimation. And even in the worst case, we can expect the quadratic speed up as in the Grover's search algorithm. So as you see, we should use as big system as possible and for computation on quantum computers. But in contrast, unfortunately, quantum computer is not very good at loading the data. So for example, if you want to upload arbitrary data onto the quantum computer by using the state preparation, as Warren said, it's not easy to do that. So in general, we should minimize the input data to exploit the quantum computer the most. That said, so in the HPC context, people sometimes use the compute bound or memory bound. So in quantum computing case, in general, it should be QPU compute bound, and the memory bandwidth is usually less important. So if you focus on some applications, if you are doing one of the applications, you're lucky because quantum computers are very good at simulating the quantum system, obviously. So there are several algorithms that can expect a quantum exponential speed up using quantum computer. And if you are not in this, if your interest is not in this list, no worries. There's some of the problems, for example, listed here, have some polynomial speed up compared to the classical algorithms. So because this is not exponential, it is categorized as the medium-term applications, but we can still expect something in medium term. Well, so as I said, quantum computers are very good at very specific tasks. So if you want to involve quantum computers, QPU should handle a task in a larger workflow in general. So today, let's take this definition of hybrid quantum and classical system. So we should focus on HPC applications, and QPUs are regarded as the accelerator of a specific subroutines where we expect some quantum speedup. Okay, with that said, I'd like to jump into the main topic today. So the agenda is as follows. First, I'd like to showcase what the Tierkreis is, and then I move on to the Fugaku installation. We are now working on deploying Tierkreis, the workflow system, into a Fugaku system together with Sato Sensei and his group as an option for all the HPC quantum hybrid system users. And finally, I will just briefly mention the perspective for the applications, especially the chemistry combined with NT-Chem, developed by Nakajima Sensei over there. Okay, what is Tierkreis in a nutshell? So Tierkreis is a workflow manager, and it orchestrates the hybrid workflows, including quantum and classical. And it can naturally support the distributed runtime system, and asynchronous data flow model is explicitly considered. So this is Tierkreis, and let me show you the details. But first of all, this Tierkreis was not designed for the HPC hybrid system originally. So we published a paper on the 2022 in the supercomputing conference, and some of the details have been changed since then, but the basic concepts remain the same. So if you got interested in Tierkreis by the end of in this talk, please just visit and read more, and yeah, that would be great. So I think all of you are pretty much aware of how the HPCs are working. So let's focus on the features of quantum computers in general, so that you can better understand the benefit of using workflow. So quantum computers are generally remote from users, unless you can put the quantum computers right next to Fugaku HPCs. And then oversubscribed, usually, unless you have the highest priority always. And as you see, some of the assumptions we made before is not very accurate. But anyway, these the features are usually we need to take into account when we use the quantum hardware. So to efficiently use both resources from HPC and quantum computers, we are taking the program model of Tierkreis and execution model of Tierkreis. I will first explain the program model aspect first, and then move on to the execution model. Okay, so this is probably the most important slide from my talk. So Tierkreis is an interpreter. Tierkreis runtime is an interpreter of the graph. So the Tierkreis input is graph, as described on your right side, and each box is some computation. And each wire or edges represents the data flow. So this is the model of Tierkreis. And naturally, we can, the data comes from the top to the bottom. So naturally, we can arrange the independent computations in a horizontal manner, and they can naturally run in parallel or asynchronously. And it allows the parallel scheduling and asynchronous once we give the graph representation of the workflow. Okay, so these boxes can represent many different things. For example, we can do just a simple addition of two float values, then built-ins are available, library functions, or some compiler task could be one of these, or if you want, we can include some Quantinuum applications like the chemistry package or some of the Monte Carlo package. And also, we can take a quantum backend as part of it. So this can be very different. So this difference will make a practical problem because the time scale is very different. Some built-ins could be finished in nanoseconds, and some quantum backend execution could take minutes, or if you have to wait in the queue, it could days, weeks, so very different. So we need to take this into account. And I also want to highlight some of the distinguishing features of Tierkreis compared to the other graph-based workflow manager. One is higher order. What does it mean? So higher order here means you can input the graph as a part of the workflow. So if someone else wrote a graph for their task, you can take this graph in as a part of your graph, right? And also you can use the structured control flow. So roughly speaking, it's the if statement in your graph. So it's also a unique feature of Tierkreis, so that you can make it easily scalable in your workflow design. So now the program model finished, so let's move on to the execution model. So due to the time constraint, I will focus on some of the representing features just briefly. So just in a simple word, worker is the actual implementation of the box in the graph. So the Tierkreis takes the graph, but it only defines the input-output relationship. So it doesn't have actual implementation, the graph itself. So we need to add some actual implementation, and this is the worker. So if you want to do some functionality, you can write the worker, and also if you have some existing package, you can wrap it up as a worker to put it into the graph so that the Tierkreis can understand. So this is the worker. And now you are familiar with what the Tierkreis is. So let me share the example of Tierkreis on Fugaku. So this is a collaboration with R-CCS group, especially Sato Sensei's group. And I'd like to showcase the Tierkreis on Fugaku as an example. So because we designed Tierkreis for usual small classical computers like laptop originally, so we wanted to start the installation of Tierkreis as a small, step by step. So our approach is to first make an MVP, the minimal viable product, and make it bigger and bigger, more sophisticated and more sophisticated. So our aim, we agreed between the Quantinuum team and the R-CCS team, is to reduce the risk, not to work. And then we prioritize rapid development, starting with very small prototype and make it bigger and bigger. And although we have some potentially useful infrastructure, we will try to reuse as much existing infrastructure as possible. For example, Tierkreis can schedule the workflow, but we will rely on the HPC schedulers, which is already quite mature as possible. And then we also prioritize minimizing the HPC idle time. And our approach is quite simple, just to rely on 2D science framework, and yeah, you can make it efficient. Okay, so how our Tierkreis runtime look like in Fugaku. So let's take this graph as an example. So this is the graph to execute the expectation value by using quantum backend, but you don't have to care about the details here. What is important here is that you have lightweight operation and relatively expensive operations. And on your left side, there are lightweight operations which are already built in their Tierkreis. So once you give the graph, it's ready to execute. And of course, the top-level parameters are given by users, so it doesn't need any actual implementation. And on the right side, there are a few expensive operations that we want to implement some efficient worker. And we also put another assumption where we have a remote worker, which is not in a HPC longing node or somewhere else. This could be in Waco, and some other expensive operations in local nodes. So let's focus on these 3 different categories and forget about the details. And if runtime starts, for example, you can imagine runtime is running in a local node of Fugaku or some dedicated server in Fugaku. And once it starts, let's exchange the information between the remote worker somewhere in the world and send the data by using the gRPC protocol, and it is processed and coming back again with the gRPC protocol. Then Tierkreis runtime receives the data, and it now dispatch another work calculation. And you can imagine local worker is somewhere in the compute node of Fugaku. Then you can use the file system, which is pretty efficient within Fugaku. So you can use this ecosystem, and within the local worker, we can just use memory communication and send the data back into the file system by using the file system into the Tierkreis runtime. So this is how we design the Tierkreis deployment on the Fugaku system, and also involving some quantum systems. And the one point I'd like to highlight is that this is not only for Quantinuum system. So in principle, you can use Tierkreis for Quantinuum system, of course, but you can also use it for IBM system, or you can use it for Weekends A system if the API is accessible. So this is pretty independent on the quantum backend. Okay, so what is the current status of the Tierkreis worker on Fugaku? So Python implementation is available, and we assume that the worker lives on HPC locking node, but it's not required. We can just move it to the other place. And it takes the native programs running on Fugaku once we could make a wrapper. I will mention this in a later part. And worker can use the PGSAV to run task compute nodes if you want. So Tierkreis is now being tested on actual Fugaku environment, and we expect to open this to the users. Tierkreis is open source, so everyone having access to Fugaku can play with this system. So if you are interested in this, you're very much welcome to use that as one of the options of the workflow system, of the hybrid system. Okay, so now we are almost finishing. So what's next? So this is still a work in progress, so I will just briefly explain what we want to do on top of this Tierkreis workflow system. So our first application target is chemistry. And our idea is to use the massively parallel quantum chemistry package NTChem developed by Nakajima sensei and his group to drive the very big chemistry calculations. And interestingly, the chemistry calculation have several hierarchy. So the big system not necessarily mean a difficult system. So HPC can take the entire system to calculate the approximately to make it as accurate as possible. But there's usually a part that is very difficult to calculate by HPC alone. So our idea is to take out such a small fragment that is spatially small but computationally very difficult. So we can use that for you can use quantum computer for this particular part, and the result is sent back to HPC to proceed the property calculations. So this type of method is useful even after the quantum computer becomes very proved to be useful in a fault-tolerant regime, for example. And the second part could be more interesting in the near term. So once we get the small fragment, we can consider how we can solve that. And we can probably think about VQE or some sample-based diagonalization methods developed by IBM or something else. This is the open question. And if you have any ideas, we are very happy to talk. So this is the current status. And this is a high-level description of the workflow for the minimal viable product. So there's nothing new, just to implement the chemistry circuit and run the VQE. And if you implement it with Tierkreis, this will look like this. I don't mean to explain everything, but just wanted to scare you. But the Tierkreis worker, Tierkreis can easily arrange the workflow automatically and automatically arrange the computation so that it will become asynchronously executed. So hopefully we can complete the workflow in development and deployment. And hopefully we can provide this as a good example of using Tierkreis so that everyone can follow and try to use that if they are interested in. So this is a work in progress. And in conclusion to this talk, so again, Tierkreis drives a workflow represented as a graph. So this is the most important thing I want to deliver. And again, Tierkreis is open source, so you can install it not only to your HPC login node, but also to your laptop if you want to try. And it is independent on backend. So again, you can use it, of course, for Quantinuum device, but also for the IBM devices if you want, just to use the existing, just to drive the existing ecosystem. And also prototype being tested on Fugaku, so we will soon be able to provide that as one of the options for the workflow driver. And as an outlook, we are thinking about chemistry applications together with Nakajima sensei, and also we are thinking about many more things. And I encourage you to use the hybrid system involving the Quantinuum hardware. And if you can also think about Tierkreis as a workflow driver, that would be present for us. Okay, with that, thank you very much for your kind attention.